Hey everybody, Professor Davis here, chemsurvival.com, YouTube channel Chem Survival, and Associate Teaching Professor of Chemistry at Georgetown University. Today we're going to do a short talk on hydroboration oxidation, how to predict the products and make sure that you get your stereochemistry right. So before we jump into the stereochemistry part, let's just review the mechanism of the reaction really briefly so we all understand exactly what the constraints are when we run this kind of a reaction. Now, the hydroboration oxidation reaction happens in two steps. In the first step, we create what's called an alkyl borane using BH3 or some equivalent reagent, and usually an alkyl ether like THF as the solvent. And in this process, forming the alkyl borane, a single concerted step takes place in which new bonds to the hydrogen and the boron of the alkyl borane are formed. So this has some interesting consequences, right? Number one is it's all happening at once from the same side of the molecule. And number two is you might notice that the borane functional group is actually on the less substituted carbon of my alkene starting material. So why would that be? Well, to figure that out, we have to look at the transition state that leads to this alkyl borane intermediate, right? And if we take a look at this alkyl borane intermediate and how it forms, right, what we see is that during that formation, in the transition state, because boron is less electronegative even than hydrogen is, that it actually works its way to the less substituted carbon due to the balancing of those partial charges that form. So keep that in mind. Anytime you see a hydroboration step in a reaction intended to form an alkyl borane, you're going to have an anti-Markovnikov addition, right? Okay, so we have an anti-Markovnikov regiochemistry. And because it's all happening at once on one side of the molecule, it's also a stereoselective reaction. It's what we call a syn addition, where both the hydrogen and the borane group, which we're eventually going to oxidize into an alcohol, are going to end up on the same side of what was originally that double bond. And because this all happens in a concerted step, rearrangements aren't possible. We don't tend to see methyl shifts, hydride shifts, or ring expansions taking place during these reactions because of this. Right? So once we're done making our alkyl borane, it's a simple oxidation, usually using something like peroxide and an aqueous base to get us to the final product, which is our alcohol. Okay, so now we understand the mechanism a little bit better. Let's think about how we can use our knowledge of the mechanism to predict the products of this reaction in a starting material that has EZ isomerism, something like this 3-methyl-3-hexene that I've got here. So the way that I go about determining which of the potential stereoisomers will form in a hydroboration and oxidation reaction is this. I take that alkene and I turn it on its side, like so, right? Just a 90-degree turn on its side. So here is my alkene as drawn. What I'm going to do is I'm going to turn it just a little bit here so that I'm looking edge on at that double bond. And what that's going to do is that's going to push my substituents either forward or backward, either out of or back behind the plane of the screen. And they're going to retain that perspective for the remainder of the process. I know this because I understand how this mechanism works. It's a concerted syn addition, right? All happening on one side of the molecule. Okay, so in order to figure out what's going to happen, all I have to do is remember the hydrogen will go to the more substituted carbon. The OH will go to the less substituted carbon, and they will both approach from the same side of the molecule. All of my remaining substituents will simply move out of the way, but they're not going to lose the perspective that I've drawn when I tilted the alkene on its side. So the reaction will progress something like this to this product. So you can see here, I've got two new stereocenters that I have created, and I have to account for that when I'm working out what the potential products of this reaction might be. So let's do the entire reaction here for this particular 3-methyl-3-hexene. Right? So here I am again, Z isomer, 3-methyl-3-hexene. I'm going to turn that on its edge, giving perspective to the substituents. They'll never lose that perspective. They're going to stay the same. If they're coming out now, they'll be coming out at the end. If they're falling back now, they'll be falling back at the end. I'm going to conduct the hydroboration oxidation under appropriate conditions, and I actually have two potential products that could form. One we've already looked at, in which you're going to have an anti-Markovnikov addition happening in a syn stereochemistry, leading to this product, 3s4s 4-methyl-3-hexanol. But I also have to remember that the hydrogen and the OH could just as easily come from the other side of the double bond, still in a syn addition, leading to instead this stereoisomer, the 3r4r4-methyl-3-hexanol. So these two stereoisomers, this set of enantiomers, would be expected to form under this set of conditions using the Z isomer of 3-methyl-3-hexene as my starting material. Now, if instead it were my goal to make the, say, the 3R 4S or the 3S 4R, all I would have to do is start from the E stereoisomer of the starting material. And as you can see, if you do the same process for yourself, you'll find that you would indeed get that set of enantiomers as your major products. So once again, hydroboration, oxidation, it's a pretty nice reaction to use when we want a very specific set of products, right? Because we know it's anti-Markovnikov. We know that we're going to get a syn stereochemistry from our addition reactions, and we know that rearrangements aren't going to be problematic. So that's how we predict the product of a hydroboration and oxidation reaction of an alkene that has EZ isomerism. Thanks for watching, everybody. Professor Davis from chemsurvival.com and the YouTube channel Chem Survival. See you next time.